Welcome back to Chapter 3, Functions of Combinational Logic. 3.4 Decoders. It is a logic circuit that accepts a set of inputs that represents binary number and activates only the output that corresponds to that input number. Input is n-bit codes, output is 2 power of n. Figure shows the logic symbol for 4-line to 16-line binary to decimal decoder with active low outputs. So we have this 4 to 16-line binary to decimal decoder. It has 4 inputs and it has 16 outputs. Active low means activate the output line 0 and the rest of output lines will be value of 1. If it is active high, the output line will be high and the rest of the output line which are not activated are low. So the enable input of pin E must be turned on for the decoder to function. The binary to decimal decoder has active low enable. When this pin is low or 0, the decoder can operate. Otherwise, all outputs will be 1 or not active. What is inside the decoder? Internal structure of 74HC154 4 to 16 line decoder looks something like this. So we have enable inputs from G1 and G2. The decoder value inputs A0 to A3, and we have 0 to 15 or the 16 output lines. So in this exercise, let's determine the output of the binary to decimal decoder in the figure when the input is 1011. So 1011 in binary is 11 in decimal. So we expect that pin number 11 will be activated. First, we need to enable the active low enable input. We give it a 0 value. And then let's start with the MSB, which is A3 1011, and that will enable the output line 11, which will be output low because it's active low, and the rest of the output pins will be 1. Sometimes not all 2 power of n input combinations are needed. This is shown in common decoders below. For example, a BCD to decimal decoder is 4 to 10 decoder, 74HC42, and we don't have 16 outputs, we only have 10 decimal outputs. And the BCD codes A3, A2, A1, and A0 produces decoding functions of until 10. The rest are not used. For a BCD to 7-segment decoder, this truth table shows that there are only 7 outputs from the 4 inputs A, B, C, D. So what happens to 10 to 15 combination? It will be X, 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 X. That means we don't care. So the truth table for common cathode to BCD 7-segment decoder, this is for active high outputs. So let's look at an example. Let's say we have 4-bit BCD input 0100, which represents the number 4 as given below, and it will activate 4 segments out of the 7 segments. This comes from this decimal digit 4, input 0100. 7 outputs B, C, F, and G are the only segments that light up. That means there will be value. So you can see that will show the value 4. Segments B, C, F, and G. So this is the LED's arrangements in the 7-segment decoder for common anode. And we can display from numbers 0 until 9. And number 8, of course, has all the segments lit up. And this is the physical view of the 7-segment used. And 2 arrangements of either common cathode or common anode circuits. Let's look at example 2 for decoders. Referring to the figure below, write the Boolean expression for x and y as a function of inputs a, b, c, d in standard SOP form, and obtain the simplified SOP expressions for x and y. So this is our circuit from the 4 to 16 decoder. There are additional 2 OR logic gates that are connected, and we need to find x and y. And we can simply do this by actually finding out for each of the 16 line decoders outputs that are connected to the OR circuit, and write the expression for x and also y. And for the simplified SOP expressions, why don't you try it out yourself? This is the 4-bit decoder decoding function. Right. Example number 3 for decoder. The specifications of the required decoder are given below. If AB equals to 0, 0, the number 0 is displayed. If input is 0, 1, the number 1 is displayed. If AB 1, 0, number 2 is displayed. If AB 1, 1, number 3 is displayed. 7-segment display unit used is of the common cathode type. Logic 1 is used to activate a segment. So build a truth table of the required decoder. Use K-maps to get Boolean equations of segments A, B, C, D, E, F, G, and draw the circuit for each of the segments. So first we need to build a truth table of the required decoder. So if input 0, 0, our 7-segment output will be 1, 1, 1, 1, 1, 1, 0. This is to activate all segments except segment G. For inputs 0, 1, segments outputs will be 0, 1, 1, 0, 0, 0, 0. And also for AB equals to 1, 0 and 1, 1, the output is as shown. Next, we need to use Karnaugh maps to get Boolean equations A, B, C, D, E, F, G and draw the circuit for each of the segment. So let's start with segment A. We can fill in this K-map with the values from the truth table, that is 1, 0, 1, 1, and then we circle out the groups of 1, and we find that the output segment A is equal to B bar plus A. For segment B, since all the segments are 1, whatever A and B value is, so it will simply be equals to 1. And just connect B with VDD of 5 volts. For segment C, there is 1, 0 in the K-map, so we can group this together. It will make it A bar plus B. For segment D, this is the K-map, and it's simply B bar plus A. And this is a circuit for D. For E, it is simply B bar. So just put an inverter or NOT gate there. For F, it's just A bar, B bar. So we need 2 inverters and 1 AND gate. And for G, we have G equals to A. So that completes our circuits for all the 7 segments for this question. Encoders. An encoder is a combinational logic circuit that essentially performs a reverse decoder function. The process of converting from familiar symbols or numbers to a coded format is called encoding. For example, this decimal to BCD encoder, we have decimal inputs of 0 until 9, and these decimal digits are coded into BCD, and the output is 4 bits or 4 digital outputs, A3, A2, A1, and A0. Let's try an example of this encoder circuit. Design of a binary encoder with priority. The description of the required encoder is given below. A is the LSB. In normal cases, if only one input is activated, if only A is activated, A equals to 1, XY equals to 0, 0. So if A equals to 1, the rest are not activated, the output will be 0 and 0. If only B is activated, xy equals to 0, 1. If only C is activated, xy equals to 1, 0. So we look at where C is. It's right here. So that's 1, 0 here. And if D is activated, xy equals to 1, 1. So if D is activated, xy equals to 1, 1. Right. For abnormal cases, if more than one input is activated, it goes by priority. A has more priority than B. So let's look at more than one input activated. A has more priority than B. So A will be prioritized. That means A will make xy 0, 0. This is also 0, 0. Look at other cases where we have A and B together. So A has more priority, so it should be 0, 0. Look at another one. A has more priority, it should also be 0, 0. A has more priority, it should be 0, 0. As well as other cases where there is not A and B, but A and C. A will still have more priority. It goes to 0, 0 here. And A and D. A is also prioritized. And this one, A and C, A is also prioritized, so the output is 0, 0. B has more priority than C, so let's look at where B and C are activated at the same time. So that means B will be prioritized, XY will be 0, 1. This is 0, 1. And let's look at another one where B is prioritized. So B and D, of course, B is going to be prioritized. So it will be 0, 1. And in this case, B and C is also here. So this will also be 0, 1. Let's look at the next one. C has more priority than D. So if both C and D are activated, right? C has more priority. That means XY will be 1, 0. So we only have one more space missing for the combination of 0, 0, 0, 0. So if no input is activated, xy equals to don't care. That means no input is activated, xy equals to don't care, x and x. Alright. Then we need to get the Karnaugh maps to obtain the Boolean expressions for each x and y. So from this truth table that we built just now, we can get the Karnaugh maps to represent the Boolean equations. And we get this first one where x equals to b bar a bar. It's because both b and a here are 0. And also y equals to b a bar plus c bar a bar. So group of 4, you can see 4 adjacent groups. 1, 2, 3, 4, and another one right here.